So as Bill said, I'm Garrett Catron, a software engineer at Facebook working on the Glow team, and I'm here tonight to tell you guys a little bit about Glow. So kind of a roadmap. First, talk about at a high level what Glow is. Then we're gonna spend a little bit of time talking about the Glow compiler, talk about Inixify, you'll find out what that is when I get to it, and the Glow runtime and execution engine. So what is Glow? Glow is an abstraction layer that sits on top of machine learning accelerator hardware. So it is a compiler and execution engine for machine learning networks that provides a single interface to a host of different hardware platforms. So why did we build it? Well, in short, we needed it, and for a couple of reasons. The typical node visitor framework didn't get everything we needed. We needed to be able to support a lot of different hardware architectures. We wanted to be able to optimize across the entire graph. We wanted to have a bag of reusable utilities to make it easier for hardware vendors to enable their platforms with Glow, as well as give it tools such as quantization support and memory optimization. And finally, scale. We wanted Glow to be able to scale up to the data center where you have multiple accelerator cards per host, and all the way down to the Internet of Things application where you compile ahead of time onto a small microchip. So let's talk about Glow as a compiler. So compilers can do a couple of things. I mean, they're good at targeting multiple different hardware platforms. They're capable of compiling intermediate representations, and they're really good at doing things like vectorizing and fusing loops, all things that we want to use. So if you look at an architecture of Glow, it looks like a pretty standard compiler. On the one hand, you have your front-end inputs, Onyx, which I think many of you are familiar with, but for those who aren't, it is an open standard for serializing a neural network. You have Cafe2 integration, which Inixify, more on that later, and we have a C++ API. Not pictured here, but we're also good friends with the PyTorch community. The Glow's GitHub is actually under the PyTorch organization. And so we're working closely to make sure that Glow works seamlessly with PyTorch as well. But then you have, in the core, you have your core compiler, optimizing, quantizer, talk about that in a little bit, and then finally code gen out to your target platform. So you can think of your optimization, the optimizations we do at three different fundamental levels. You have your high-level optimizations, which are really reasoning over the entire graph. You have then your lower level optimizations, which are reasoning over memory access, memory use, buffer reuse, and lower tuned. And finally, you have backend specific optimizations that can be enabled on a per platform basis for each different hardware architecture. So let's talk about some of those graph optimizations. Here, we have really two categories. First, you have your domain specific. So this is things like fusing a batch normalization and a convolution, or eliminating redundant transposes. But then you also have more classical compiler eliminations, dead code, common sub-expression, and constant propagation. Some examples, here you have a constant in the top left, which is being transposed before being passed into its next operator. So if that constant is only being used by that operator, why don't we just transpose it at the beginning at compile time, and that saves us a transpose at runtime? Or you have transpose into transpose into transpose. It happens sometimes with different larger scale operators. You can remove two of those transposes, saving you valuable compute cycles. So we then move from the graph level to more of a lower level. And the reason for this strategy really is scalability. So your typical machine learning frameworks like TensorFlow or PyTorch tend to have hundreds of different operators. And if we want support for many different hardware backends, each one with its own unique assembly, this very quickly gets out of scale as a support surface. So instead, we lower these complex operators down into a smaller subset of simple operators, such as division, multiply, add, etc. And then you only have to map these to the hardware platform. It gives us a much simpler space and allows us to scale much more readily. Also at the lower level, we can, sorry, my animations are a little off. We are able to do things like stacking kernels. So quite often, when you're operating over a tensor, you're doing an element-wise action. So first an add, then perhaps a multiply, or something else. And so you wind up going through each tensor, and this really thrashes your cache. So Glow can stack those kernels together so you can do multiple actions in a single pass, saving your cache, increasing your overall speed. And finally, Glow supports ahead-of-time compilation so that you can compile your network down to a binary and then run it without needing to go through Glow. So this is particularly of interest for, particularly of interest for the Internet of Things application. Low power, where you can't compile on the fly. And Glow emits debug information. So when you want to walk through your network to get an idea of what's going on, we emit debug symbols that you could launch with something like LLDB at the low-level IR to see what's really going on. So let's talk a little bit about Anixify. Anixify is an interface and protocol for interfacing deep learning frameworks with hardware backends like Glow. Particularly, we use it to interface Glow and Caffe2. And so what this really means, or the core problem that Anixify is solving, is say you have a given neural network. Some operators you want to run on the accelerator because you'll get the increased speed, increased performance. However, some operators just are not going to run on hardware. In PyTorch, you have operators that do things like, based on some input, go fetch from a URL. Many of your accelerator cards don't even have a network device. They simply are not going to support an operator like that. So here's where Anixify comes in to partition the graph in what's going to run on the host and what's going to run on the card. And we do this with the following process. We first walk a given network, and for each operator in that network, Anixify wraps it as its own single operator Onyx network and passes that into Glow, where Glow does a lightweight compile to determine if that operation is supported on your target backend. If it is, it returns up. If not, it still returns non-supported. Anixify then groups these operators together so you have connected subgraphs of what can run on the host and what can run on the card, and then passes the entire connected subgraph to Glow to compile and load on the card. So let's walk through an example of what that looks like. So here we have an example Caffe2 network with 5 ops. Let's imagine that 3 of those ops, colored green, can be accelerated, and 2 of them in red will not. So after calling is op supported on each op and determining that it is or is not supported, we next group those into this Anixify op. So I'll use Caffe2 as an example here. Caffe2 then treats this operation as a single node in its graph, and it just simply passes it down to the accelerator, gets its outputs back, continues to walk its graph until it comes to another Anixify node, and finally gets to the output. So this sounds great, but there are a few constraints that we're still working on solving. First, static shapes. Most accelerator hardware architectures do not support dynamic allocation, so they need to know the batch size and the size of all of their tensors up front. This tends to be a bit of a challenge, shall we say, for things like PyTorch and Caffe2 that prefer dynamic shapes. You can change the batch size on the fly. So the way we currently get around this is you set an upper bound when compiling with Glow. You can still have your dynamic shapes in PyTorch and Caffe2, and Anixify handles the tensor refitting when it goes into Glow in the hardware. Another complication is quantization. On the CPU, we tend to run at FP32, floating point 32 precision. Most hardware accelerators don't support FP32, and those that do see a fairly sizable reduction in performance. So you really want to quantize your model down to, say, FP16 if you can't go any lower, but preferably int16 or even int8. To that end, Glow provides a toolset that allows you to do a basic linear quantization to either int8 or int16. And it does this by first instrumenting the graph and running through it with its interpreter backend, building a histogram for each node that it can then use to set the scale and offset for each row in the graph, which it outputs as a quantization profile. You're now ready to run your network, quantize on the hardware, but you can continue to fine-tune your quantization to get that last bit of precision that you need. So with that, we're ready to talk about running on hardware. So the execution engine is responsible for providing a host level abstraction. It's responsible for managing multiple cards, managing the compilation of networks and loading them across those cards, and then handling concurrent inference requests. So it looks something like this. You first load your network, you provide the model, you load the network and constants onto the card, and now you're ready to just throw requests at the hardware. So if we look at it from an architectural point of view, it kind of looks similar to the compiler. You have your inputs on the left, an XFi, Cafe2, the C++ interface. But now we have this host manager. And that host manager is that host level abstraction and interface into Glow. It's comprised of four main components. You have the partitioner, the device managers, the provisioner, and the executor. These then go out and interface with the hardware accelerators. So let's talk about the device manager. The device manager is a host level abstraction for a specific hardware card. So it is responsible for managing a single device, tracking memory, loading, offloading, and running execution on the card. So it has an interface like this. You load your network, you can call an execution, it copies inputs, and when it's done, returns outputs. And additionally, it tracks device statistics, available memory, current load, device health, and other counters so that you really know what the state of your device is. So next, let's talk about the partitioner. So this is important in the case of a large network. Sometimes your network is going to be too large to fit on a single card. This is where the partitioner comes in. It divides the graph primarily due to constant size weight, but it also takes into account communication costs, trying to minimize jumping back and forth in and out of different accelerator cards, as well as minimizing execution time if it can. An example as follows. The graph in blue, you have those three nodes that are circled. Those are all constants. Imagine each one large enough that no two of them can fit on a single card. So we first break out one of those constants into the middle graph where you have red and green. But the green graph is still too large to fit on a single card. So we split again. Now we have three independent subgraphs that can be loaded on three separate cards, and we can run our network. Once we have our partitions, we move on to the provisioner. The provisioner takes those subgraphs and actually assigns them to a given card based on available space on the cards currently, as well as current load on the cards. It's responsible for actually then compiling the subgraph for the target platform and calling into the device manager for that card to load the network and get it ready to run. Once we're provisioned, we're ready to execute. The executor walks the new graph of subgraphs, handling interdependencies and executing. For a given graph, it converts the subgraph to a schedule. In this case, you have G1 and 2 have no opening dependencies, so they can be kicked off in parallel. Once they're both done, G3 is ready to be kicked off, and so the executor copies the outputs into the inputs of G3, and finally G4 before returning up the stack that your network is complete. So that was one system. This is a slightly more complicated situation where you have multiple devices, multiple networks loaded, and several in-flight requests. And so the scheduling can get a little interesting. So we start to ask questions like, were our partitions created well? Did we provision evenly by load? Are we scheduling optimally? And here, we've got some room for improvement. You can see on device 1, A1 is blocking the kickoff of A2 on device 2 being in red. And so you can see on device 2, we have these gaps. That's performance we're losing because the device is not saturated. So to track into that performance, Glow also supports trace events. We export in the Chromium trace events format so that you can see what operators took the most time in your execution and where you were waiting, and get a feel for the overall performance of your network. And you can do this by either manually inserting trace events at specific points, or we support auto profiling, where we insert a trace event for every single operator in your graph, and you can see the entire trace. So to sum it up, you have an execution flow that looks something like this. On the network adding side, we have a front end calling in to add a new network. That's passed to the partitioner, where it is split into its subgraphs. The provisioner then takes over and assigns these to specific hardware devices, compiles, and calls into that device manager to load the network. Once all of them are loaded, you're ready to roll. We then wait for an incoming inference request. The host manager creates an execution graph with the intermediate storage to hold intermediate results and hands that off to the executor, which kicks off any subgraphs that have no outstanding dependencies. And it does this by calling into the device manager, which loads the inputs, kicks off execution on the card, copies the outputs back, and signals to the executor that that piece is done. And the executor continues to walk all of the subgraphs until every subgraph has been completed, at which point it signals back to the host manager that we're done, and we can return the results back up the stack. So that's what I've got. Thank you guys very much. And I think I talked a little fast, so I probably have plenty of time for questions.
Yes, so let's see one of in the back first.
Thank you for the presentation. Excellent talk. I'm curious about which model were you running that needed splitting. The largest GPU today can handle the largest network we have seen. The largest I know is 1200 layers. So can you explain as to which model did you run and why did you need to split the graph across GPUs?
Sure. So a lot of the current models out there, especially like computer vision, tend to be smaller and fit very readily. But we have a lot of internal models that we use that are significantly larger than what would fit on a single GPU or even a couple of GPUs. So I can't go into too much detail there, but we have a lot of internal models that definitely need to get partitioned.
Hi there. So on one of your earlier slides on the backend saw some vector instructions. Can you mention what backend on the vector instruction that you guys have found productive and effective, as well as what vector instructions for a backend that you would want to have?
Certainly. So the easiest one that comes to mind is we have a reference CPU backend, and we definitely do vectorization there. And it backend manufacturer. And so some that are more CPU-like in their execution, you can get wins on vectorization. Others that tend to have specialized matrix multiplication engines, you're not going to vectorize, you're just going to throw the matrix at the engine. I don't know if that really answers your question. Sorry, what was that again?
What would you like to have in terms of how big the vectors, how much of the pipelining, and how many stages? Like, even though you may not have it today, what would you like to have in like?
I mean, whatever saturates the hardware. We can chat more offline if you have more questions.
Let me give some chance to the other side. Okay.
So you mentioned how you wanted to use multiple GPUs to fit, let's say, a really large model. What happens if you want to do some data parallelism and you want to have multiple versions of the model running different batches, and maybe you have some sync training to perhaps support large batch size training? Does the framework support any of these kind of features?
Yeah, so let me break that down in a couple of different directions. I guess the first side is perhaps you want to run the same model replicated across multiple devices, and we do support that. Currently, it's basic support. It will just you can tell it to saturate your host, but we're working on improving that support. So we have that. On the training aspect, Glow so far has been written with inference in mind, but we are hoping in the next year to add better training support. The difference there really is with training, you have your intermediate weights, and there's a lot more card-to-card communication. And so we're doing some re-architecting to really make sure that's not a bottleneck.
I mean, your talk was awesome. I was trying to follow it. Like, it's good. So my company, as of now, like, we are using PyTorch, right? So we have a model. Like, example, you just mentioned that you have a specific model. So I'm trying to create a pipeline based on like where PyTorch, Glow, um, any cloud provider like fits in over there, right? And we are basically trying to solve the model like multiple GPUs together, right? So that being said, so if I have a model and right now it's customized. I mean, what I meant is like internal for us, right? As of now, maybe hopefully you get my question is, I want to use Glow as of today, right? Right now, maybe like another week. So is it, first question, is it open source?
Yes, so Glow is GitHub, PyTorch, Glow, I believe. I should have put the URL up on one of my slides, but Glow is absolutely open source, and our goal is to make it, we want to support the entire industry. We want it to become an industry standard. So you can go on there, grab it. We have examples in Glow that are running, for example, we're running ResNet 50, ShuffleNet, English to German. And so, and there's a model loader in there that you can then try loading your model. If you can serialize it to Onyx, the model loader can try loading that up. And then it really comes down to just a question of operator support. And you could run it on any of, we have 3 backend, actually we have 4 backends in the repo now. We have 2 different CPU backends, an OpenCL, and then Habana just open sourced their implementation as well. So if any of those backends, you can try running your network and get a feel for operator support. And if you find operators put up an issue, put up a PR, we're always happy to accept PRs.
And second question is about to grab. Yeah, sorry. The thing is, like there is something breaking thing, like, where we came up with Glow. So if you don't mind, like, what is it? It made that like Facebook, like company like a Facebook, they came up with Glow.
Sure. So I would say the biggest value of Glow is really, it's twofold. It's an optimization. So the compiler, we do a lot of machine learning at Facebook, just like every other company up here in the Bay, and that costs a lot of money. So we want to cut costs. But the other big thing is the flexibility. If you can marry your software stack with Glow, you can then change hardware and you don't have to worry about vendor lock-in. So currently, Habana has a nice card on the market. Tomorrow, another vendor may come up and you go, hey, they've got a better price point and performance. I can swap that out, make sure Glow supports that, and everything up the stack sees no difference.
Second, let me give the other side of the, have some chance to ask some questions.
What do you think about like large, I guess, proprietary graphics cards and other accelerator like makers that I guess are really unwilling to share like source code for their compilers and whatnot?
Well, I suppose you can tell what Facebook's approach is by the fact that we're open sourcing and pushing Glow so hard. So in a lot of ways, it's kind of make it a win-win situation. And that's the goal, that's why Glow. We provide a lot of common tooling in the compiler, so any hardware vendor, we make it easy for them to plug into our stack and hopefully gain wins. And this way, and if there's a user base, okay, well now they get that interoperability. It's kind of get it going, get people, we're going to be using it. And so, I mean, we're going to try to make it a pretty good product if we're going to use it. Hopefully others find it the same way. And that's really our goal here. Mm-hmm.
Thank you. Do you know what AdaNet is?
AdaNet?
An open source model compiler from Google, one of your neighbors.
Yep.
I'm wondering if you feel like there's a possibility for doing cross-validation across AdaNet models. So if somebody has a large data set and they want to figure out which model is the best, they can get maybe confidence intervals. Do you think that's a possibility, confidence intervals?
So if I'm understanding your question, really running a collection of different models across the same data set, really to get your, I don't see why that would be difficult. I mean, that's really, I don't think we have particularly the framework to do that, but you could build it on top of Glow. So if we have, I guess I'm not really tracking your question. I'm afraid I can't answer that question. I'm really more of on the language side. I'm a beginner in the machine learning realm.
Any question for this side before I run into the other side? Last chance, no more. Okay. Sorry, you lose the chance. Okay, let's get a couple of questions.
We can chat afterwards, and maybe I can help iron it out.
Hi. It's a great framework for doing all of the machine learning quantization and pruning. My question to you was, you spoke about breaking down the model and pruning the models and quantizing it at 16-bit and 8-bit precisions. In your experience, what was the loss of accuracy and what was the gain in performance when you are targeting different type of GPUs and different accelerator cards? And when you integrate Glow with other accelerator providers like FPGAs and others, how do you make sure that you are giving the similar kind of optimization experience across different platforms?
Sure. So there's quite a few questions in there, so I'll try to break down the ones as I recall them. So first I'll talk to the precision loss and performance gain. That really does vary across different models. For models that are more compute bound, you tend to see a very significant increase in speeds, like ResNet 50, quantizing it down to int8, even on a CPU, I believe you see something like a 25 to 30% speed up, which is pretty good. And you only saw I want to say it was about a 3 to 5% reduction in accuracy. And this can be alleviated with quantization-aware training and tuning your quantization parameters. So that, I think, gets to that first piece of it. As for making sure we provide the same optimization across different hardware platforms, so a lot of our optimizations we do, so that's why if I had the slide where you had sort of those 3 tiers of optimizations, at the graph level and the IR level, those are device agnostic. And so any device integrated with Glow gets all of those. And then you have whatever special sauce you as a hardware maker want to add in that says, hey, by the way, my card is really, 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 really good at convolution. So anything you can fit into a convolution, that's what's going to make my card most performant. We give that flexibility in the back end per hardware platform.
Any other questions here? Okay, let's take the last one.
What can you say about mobile? I mean, your host manager and execution engine in the future, I think Facebook is very strong for on mobile execution.
Right. So really the host manager I view mostly as coming into play in the data center world. On mobile, you're likely to have a single accelerator chip, and so you go more of the ahead of time compilation route. We're still working out more of a multi-chip ahead of time compilation model, but we plan to support that. And in that case, then it would be a much simpler, lighter weight model. Does that answer your question? Thank you.